Good. So here you go. October 17, 2022. We finished chapter 5. We're going to start chapter 6. Chapter 5, you gotta study all the sections with, but section 5.5. Okay, everything else you should worry about, but 5.5. Today we're going to start chapter 6, which covers the idea or concept of work and energy. Okay, the idea of work, the idea of energy depends on the idea of work. So first we cover work and then we cover energy. So far, exam 2 is scheduled for November 2nd. And before we start with the idea of work, now just remember that so far we have used the idea of force to solve problems in physics. When you solve problems using force, when you solve problems using the concept of force, which by the way is a vectorial quantity, you need to do the following. You need to do the following. 1, make a simple drawing of the physical problem, right? Identify all the forces acting in the object. 3, use the, after you identify the forces acting in the object, use a free body diagram. Use a free body diagram. Identify all the forces acting on the object. Use a free body diagram. 3, use Newton's law of motion to solve the problem. That's what you do. Okay. Okay, now the concept of work, the idea of concept of work, the concepts of work and energy can also be used to solve the same problems that we solve using the idea of force. Okay. The difference, very, very important. The difference being that force is a vectorial quantity, whereas work and energy are scalar quantities. Okay, scalar quantities. That's the important difference. So now you have to ask yourselves, right? You have to ask yourselves. So if you have the choice, to solve a given problem using either the idea of vector, or if you have the choice to solve a given problem using vectors, right? Or using scalars, what do you think is going to be easier for you, right? Think about that, right? Remember, it's much easier to solve a problem using scalar quantities than solve a problem using forces, right? Because forces, it's going to, a given force or a given vector can have up to 3 components in the 3-dimensional space, whereas a scalar has just a single component, right? So that's why we introduced this idea of work. That's why people came up with this concept of work. And how does it go? And how does it go? How do we introduce that? So it's like using the idea of work and energy. It's like solving the same types of problems in a different way. Okay, force versus work. All right, 2 different ways of solving the same type of problem. So how do we introduce the idea of work? Okay, so we start here with a object sitting down over a surface, and we have this block, we have this force being applied to the block. Let me simplify the drawing, right? So you can, in this case, in this case here, we start with the X and Y axis first, and then we put an object here, right? There you go. Consider a mass sitting in the XY plane. Okay, and this mass, this object, is subjected to a force. Let me erase that. That for now, you're not going to need that for now. Okay, subjected to a force, whatever direction it is. We need this introduction before you understand the idea of force. Okay, of work, the idea of work. So what happens next? Okay, because this object is subjected to a force, it may be able to move, right? And in this case, this object is moving at distance d. The force is not changing as the object moves. So here you go. And I can even state that the object is displacing a delta x, amount given by this vector that you see here. So instead of d, I'm gonna write that down as delta x. Take out okay, so the vector. So we have this vector force and we have this vector displacement delta x. How do we define the concept of work? Okay, we define the concept of work in terms of the force applied and the delta x. Okay, so the definition, the specific definition is, let's go back to my notes, is something like that. Is the component of the force along the displacement times the displacement itself. Okay, that's how we define the work done by a given force. Okay, work done by force F. You gotta memorize this relation. Okay, so let's apply some simple examples, right? If the force has the same direction of the displacement, what does it mean? The angle theta equal to 0, angle theta equal to 0, right? The work done by force F becomes F delta X. And I'm going to emphasize that is going to be the magnitude of F and magnitude of delta X. Okay, very important here. Here you go. If, here you go. This, instead, right? Instead, if the force acts contrary to the displacement, then it's possible to have something like that, okay? In this case, angle theta is equal to 180 degrees, okay? Then the work done will be, here you go, F cosine of 180 degrees, right? Times delta X. And again, you're still going to have the magnitude. The best way, okay, is to, the right way would be to put magnitude here. I should have put magnitude. Because what determines the sine is going to be this angle theta, the cosine of theta. Okay, so here you go. So if the force is anti-parallel, you know, contrary to displacement, you know, in other words, force is anti-parallel to the displacement, which means the angle theta is 180 degrees, then the work done will be equal. The work done is going to be a negative quantity. Okay, just a little practice here. So here you go. Here's the most genetic case for the work. Here's the most genetic. We don't need this picture anymore. Okay. Here's the simplest case of work. And again, there's a little mistake here in this figure. Okay. Work in the same direction as the displacement. And then we can have other cases. Let's see, I'm going to illustrate the case of the work being negative, right? I'm not going to put values there because I want to treat, I'm going to put like this way. Force anti-parallel to the displacement. You go. Go. And parallel, we go delta X. Delta X here too, right? It's important that we define that as a vector. And then we have that other case. Suppose that the force is perpendicular to the displacement. That's another special case of work, right? Like the weight, right? The weight is perpendicular to the displacement in this specific figure, right? So instead, another example. What if, what's going on here? My computer is misbehaving. Let's see here. Okay. It's just saving it, not responding. Huh? Ay. My computer is not supposed to behave like that. This computer is not supposed to behave like that. What's going on here? Bear with me, please. Task manager. Can you still see my screen, by the way? Let me quit as as much stuff that I can. Let's see if it's still misbehaving. Yeah, still misbehaving. Okay, good. Now it went back to normal. Good. Good. Okay. Now let's see. Now, what if oh man. Okay. Go. What if the force is perpendicular? It's perpendicular to the displacement. Just apply the definition. Okay? Just apply the definition that you're supposed to apply. Okay? Work will be 90 degrees. Okay, cosine of 90 degrees is what? Is 0, right? So the work done by a force perpendicular to displacement is going to be 0. Work done by a given force. Okay. So that's what you have to know about the force. What's the unit of work? The unit of work is going to be the unit of displacement times the unit of force. It's going to be Newton meters. And by the way, Newton meters is a unit that appears so frequently in physics that we call it the joules. Okay, so that's the unit of work. I can go even further and here write this unit of joules in terms of the main SI units, right? Kilogram meter per second square for force times meter. When we multiply meter by meter, it becomes kilogram meter square per second square. Okay. So this is the unit of joules. And by the way, joules is both a unit of work and also a unit of energy. Okay. The kilowatt hour that you see in your electric bill is a unit of energy as well. And you're going to learn and you're going to see that very soon. Okay. Have you heard of the unit kilowatt hour? Unit of kilowatt hour shows up in our electric bill. Okay, you spend X kilowatt hours in a given month, right? My estimate that if 2 people living in a house using air conditioning, you should spend watching TV, right, and using electricity. You should spend roughly, depending on the time of the year, right, anywhere between 200 to 500 kilowatt hour per month. Can go to 600 if you use too much air conditioning. All right, the air conditioner spends lots of energy. Your refrigerator spends lots of energy. If you have an electric boiler that at home to warm your water, electric boiler also spends lots of energy. What doesn't spend lots of energy is your microwave oven, your computer, your TV. Okay, those they don't spend lots of energy. But what spends lots of energy is your refrigerator, okay? Because the refrigerator is like an air conditioning. It's not actually the opposite of an air conditioning, right? The air conditioner spends lots of energy. No, refrigerator, air conditioner, and your electrical boiler. And if you have an electrical oven too, I'm talking about electrical oven, not the other type of oven. The electrical oven with a resistance, right? They spend lots of energy. Okay, here we're doing a numerical example, right? A force of 1 Newton along the horizontal force of 1 Newton. Blocks displaces horizontally. Block displaces horizontally, 1 meter. Okay. What's the work of this force F? Okay. Consider the object of the previous example is the same displacement. Determine the work done by the weight. Right? So here you go. In this example that you see, it can be, remember, let me give you an example. Here you go. We have this situation here, right? The delta X here is what? We did this example there is 1 meter. The work done by this force F during the displacement is going to be 1 joule. But while this force is acting in the body, you may also have, you are going to have simultaneously the weight also applied to the object, right? It doesn't matter what's the value of your force with 1 Newton, 2 Newtons, this weight is always going to be there. So the work done by, although the work done by the force, this force of 1 Newton is going to be 1 joule, the work done by the weight is going to be 0 joules. Okay? Similarly, the work done, not by the weight now, but the work done by the normal, which by the way is anti-parallel to the weight, is going to be 0 as well, because this normal force is perpendicular to the displacement. Here you go. And then you can come by and say, look, you can have another force in there. Okay, if there is no friction whatsoever, it's a frictionless surface, there is no friction dragging this object, trying to drag this object, right? But if you do have friction, a frictional force, here you go, I'm going to put this one right in here, acting on this object, here you go. And I'm going to put a red color so it's going to be easier to visualize that. Here you go. Frictional force. Frictional force we usually represent by the lowercase f. Go. Right here. The work done by the force of friction in this case is going to be negative. Make sense? So the definition of work depends on the force. If the work done by the force F is a value, the work done by the force by the weight is another value. The work done by the normal may be a different value as well, and the work done by the frictional force in this case is negative. Okay, it all depends on the value of the work is all going to depend on the displacement and the force and how it acts in the object. Any questions about that? So let's see, we have 21 students already. Let's take a little break here, 9:20. I'm gonna take attendance, okay? So you can digest this idea of work. And you're going to see how useful it is, okay? Jade, are you there? I don't see Jade there. Vanessa, are you there?
Here.
Thank you. Makin, thank you. Ashley. Let me see if Ashley is here. I don't see Ashley. Next one is Fisher.
Here.
Thank you. Blessing.
Here.
Thank you, Janet. I don't see Janet here. Okay, Raymond. Raymond just joined us, right, Raymond? Are you there? Yeah, thank you. Lily. Lily didn't come today, right? Nor Michael. See here. Yeah, Lily and Michael are not here. Wendy. I don't see Wendy in my list. Joshua Jimenez.
I'm here, Professor.
Thank you. Let me raise the volume here. That's very low. Bethany. I don't see Bethany here. Luis Lapida. I don't see Luis either. Ana Gabriela Lopez. Nope. Basilio Lopez. Thank you, Basilio. Bahag. I thought I saw Bahag here. If you can't hear you, Bahag, I'm going to put a star here. I see Bahag my list, but I can't hear him. Next is going to be Daisy Mariscal. Thank you, Daisy. Another student is joining us. Let's see here. Janet. Alejandra Marmolejo. I don't see Alejandra. Amarilis.
Here.
Thank you. Yesenia Montes Rodriguez. Thank you, Yesenia. Mary Okiki, right?
I'm here, Professor.
Thank you. Ryan Ong.
I'm here.
Thank you. Artur Pacheco. Thank you, Artur. Alejandra Perez. Jennifer Alejandra Perez. Good. Thank you. Lady Lud. Lady Lud, yeah. Okay. Lady Lud, Jennifer. Lydia Rosas Buenrostro. Good. Thank you, Lydia. Donia. Donia here. Donia, okay, I see Donia in the list here, but I don't hear her. Okay, if you can hear me, Donia, I cannot hear you, so you can send me a text message. Elika. I don't see Elika either. Brianna Valencia. Good, thank you. Mia Villalobos.
Here, Professor.
Thank you. And Justena Youssef. Justena is here. I don't hear from her. Are you there, Justena? Okay, thank you. Let's see how many students. $19, $21. Let's see. There looks like there's one more student here who was not called. Vahad, are you there, Vahad? I see that there are 22 students participating here, but only 19, let's see, 19 plus the other two, right? That didn't answer, 21. Janet. What's your name? What's your last name, Janet? Garcia. Okay. Must be you. Yeah, that's you. Thank you, Janet. Good. Now we're in good shape. 20, 21, 22. 9:26. Let's see. Let's go. Let's continue here. Right? So now we're done with the attendance. Let's go for another half an hour. 25 minutes before our break. Okay. So that's the simple idea that you have to remember. the work done by a force. Here you go, chapter 6, work and energy, work done by a constant force. That's what we just did. That's what just covered. What comes next is the work energy theorem. Okay, here you go, that's the work done by a force, right? The guy propelling a car with his own muscle. Here you go, here's the case of the work done by a force that makes an angle with the displacement. You saw something similar in my drawings. Okay. And then we have again, here you go, the work done by this muscle man, right? He's doing work against the force of gravity. And so here you go. Another case here. Now, what we're going to do is we're going to cover the work kinetic energy theorem. Okay? Zero joules horizontal force. Here you go. Work done by the force of friction. Okay. So recall that we can have 4 forces. In this case here, we have 4 forces being applied to this object, right? Because we have 4 forces being applied to this object, we have the work done by this force, we have the work done by the force of friction, we have the work done by the weight, we have the work done by the normal. In addition to have the work done by each of those forces separately, we can also define the work done by the net force. And there is something neat about the work done by the net force. There is something neat about the work done by the net force, okay? It happens that the work done by the net force has a very special property. That's why we talk about it. We know that the work done by the net force can be a predictor of the velocity of the car. Okay, and it's also related to what we call a special type of energy, the energy that we call as the kinetic energy. The work done by the net force is related to a special kind of energy that we call the kinetic energy. Okay, so let me tell you how does it go. Okay, so here you go. Just remember that net force, right, is equal to mass times acceleration, right? Just remember that. But also remember, you know, we covered that in kinematics, that there is a relationship between the acceleration and the velocities, right? Remember this relationship here? That's the Torricelli equation. Okay. And then we can here write our acceleration. Let's here write this. Here you go. We can here write our acceleration as being what? V square minus V naught square. V square minus V naught square over 2 delta x, right? 2. Why am I doing that? There's a reason why I'm doing that. There's a reason I'm doing that. I'm doing that because there's an acceleration here in this equation for the net force, right? And I'm going to here write that in scalar format. That's a neat, something neat that's hidden in this definition of work. Okay, now I'm going to write that down just in terms of a scalar quantity. Okay. So recall that if we multiply this value here by delta x, we end up canceling out the delta x on the other side, right? And look what we get. We get something here that's related to the velocity. Here you go, half of m v square, final velocity square, minus half of m initial velocity square. Like that. Did you notice that it's kind of one of those things of physics that happens, and we find that there is a neat relation between, by the way, what you see right here is what? Is the work of the net force, right? The work of the net force. The work of the net force is related to the velocity and the mass of the object. Okay? What you see right in here, you know, since work has units of joules of energy, right? What you see right in here is also going to have units of energy. And because we have this velocity written down here, this type of energy, we give it a name. We call it kinetic energy, okay? And that's what we call the work kinetic energy theorem. What you see above is the work kinetic energy theorem. This is a theorem that works for any type of motion. And that can be proven mathematically, okay? Type of motion. Even though we used an equation for uniformly accelerated motion, in reality, what you're getting right here applies not just uniformly accelerated motion, but to any other type of motion. Okay, even to circular motion that's not uniformly accelerated. That's one of the neat things of physics. Okay, so this guy here we call the kinetic energy. Kinetic energy. Energy due to motion. The above is called the kinetic energy, or energy due to motion. Okay, so what you end up having here is the final kinetic energy minus the initial kinetic energy. Okay, so here writing that. Okay, here you go. Net, the work done by the net force is final kinetic energy minus initial kinetic energy. Or we give it a name, you know, we write that as delta KE. Delta KE. See, like that? Yeah, looks better, right? And it's possible to prove that the thing holds even, okay, even for motions that are not uniformly accelerated. Okay, let's write it down. The above relation holds for any type of motion, right? Yeah, I already wrote that down. Yeah, any type of motion, whether it is uniform motion, uniformly accelerated motion, non-uniform accelerated motion, etc. etc. We just don't prove that here because it involves it because it involves calculus-based physics, okay? So here we go. So if an object is at rest, it has no kinetic energy, right? Because its kinetic energy is 0. And just like I mentioned to you, the unit of kinetic energy is going to be what? The unit of mass times the unit of velocity square, right? The unit of mass is the kilogram. The unit of velocity square is meters square per second square, which, by the way, is kilograms meter per second square times meter, which is newtons times meter, which is joules. Okay, so the kinetic energy has the same unit as the work. The kinetic energy has the same unit of work. Okay, we don't need that, okay, because we already did it. Okay. So this relation is so important that we give it a name. We call the work kinetic energy theorem. We can come up with some neat examples. What time is that? 9:35. We still can go a little bit longer. You have 15 minutes. Let me give you an example. Okay. An important practical example. Okay, so here you go. Okay. Car example. Using the work kinetic energy theorem. A car moving with the speed v, you know, a car is moving, let's see, a car is moving the freeway, in the freeway with speed v. The driver then applies the brake and comes to a full stop. So full stop in a distance d, okay? And you picture that? You know, you're moving this freeway, let's say at 60 miles an hour. You see something dangerous in the freeway right in front of you. You slam on the brake of your car. The car is not gonna stop instantaneously, okay? Every time you brake your car, even if you slam the brake of your car, the car is gonna, the tire is gonna make a screeching sound, right? Because of this friction with the freeway, and then it's gonna uniformly, then it's gonna come to a stop after a given distance d, okay? What would be the new distance, the new stopping distance, right? Stopping distance if the car was moving at twice, at 2v, at twice the speed, right? At 2v, at twice the speed. Okay? Solution, right? By the way, you can solve this problem. You can solve this problem using the work kinetic energy theorem. You don't need to know the force that's applied to the tires. You don't need to know the force of friction, right? All you need to know is the work kinetic energy theorem. Think a little bit about that, okay? I'm gonna give you a little hint, right? First situation, speed v, okay? The work of the net force, right? We go the work of the net force is going to be given by, let's see, let's write down this one here. Going to be given by something like that. Final kinetic energy minus initial kinetic energy. Well, you know that the car is gonna come to a stop. Because the car is coming to a stop, the final velocity of the car is gonna be zero, right? If the final velocity of the car is zero, then the final kinetic energy is gonna be zero as well. The initial kinetic energy is just that value that we talked about, half of mv squared. Note that in this specific case, the work done by the net force is going to be negative. Let me do a drawing here. Go. I'm going to illustrate. Let me see if I already have an illustration here for you. It doesn't look like I have it. Yeah, so I gotta do that from scratch. Yeah, here you go. It's gonna be something like that, right? It's gonna be something like that. You have normal and weight applied to this guy, right? There's no 60 degrees. It's a flat surface. Well, I have this guy here. Here you go. We have this force of kinetic friction applied to the object. We have this initial velocity v. That's how we illustrate the problem, right? Initial velocity v. And then we have this final velocity, zero. V final equal to zero. Okay, when the object comes to a final velocity zero, we cease to have a force of friction, right? There's no force of friction whatsoever. None. Font, subscript. And now I can erase my force of friction because the object is at rest. And that's the stopping distance d. So I'm asking, what if we had a different situation in which the initial velocity was twice v, right? What would be the stopping distance of the car? We can find that out using the work kinetic energy theorem, right? Going back here, we go. Second situation, right? The speed is 2v. Initial speed is 2v. I'm even going to, okay, write that down like that. You already know that the final kinetic energy is zero. But now my v here, and by the way, I'm gonna put w prime because it's gonna be a different result. And here I call it also v prime because the different velocity, right? V prime square. Let's put it this way, yeah, v prime square. We call it v prime square. Okay. What is going to happen? You know, v prime is going to be equal to what? V prime is going to be equal to 2v. Do you agree with that? Okay. So when we square the 2v, we get something interesting. We get 4 times v squared. And 4 times v squared times m divided by 2 is going to be 2mv squared. Okay? So now we have two different kinetic energies. For the first situation, the work done by the net force is minus half mv squared. And for the second situation, the work done by the force, by the same force, by the way, everything being equal, okay, is going to be different. It's going to be fourfold what you had here before, okay? You know that this is stopping distance here. You know that the first stopping distance here is going to be d. So now we can rewrite that as being, you know, F net times d, right? It's going to be equal to minus half v squared. And here we are going to have the same force because nothing has changed. You're still using the same brakes, the same cars, times a different distance, d prime. I know d. Okay. I do not know F net. I do not know M, but I do know M. I do know V. But I just want to know d prime. How do we solve this problem? We use those two equations to solve the problem. Okay. And how does it go? Okay, you divide this equation by the other one. Another way to do it is to solve for the net force too. That's another way to do it. Okay, here you go. Let me show you how. It's just a matter of applying a mathematical technique. There's more than one mathematical technique that we can use to solve this problem. One way to solve this problem is to write F net using the first equation. Once you write F net using the first equation, we can substitute right in here. Go. And then what happens? M cancels out with M. V squared cancels out with V squared. The negative sign here cancels out with this negative sign here. And we solve for d prime. I still can repeat if I want the previous equation. Okay. To get what? 4d. Okay. So look what an interesting result. By doubling the initial velocity, we end up quadrupling the stopping distance. Okay, that goes against what we would expect, right? We usually would expect that if you double the velocity, the stopping distance will be the double, right? But that's not how it works. The work kinetic energy proves to us that the distance is not going to double, but it's going to quadruple. That's because of what? That's because the fact that the kinetic energy is a function of the square of the speed. If you double the velocity and put it here in the square of the speed, the kinetic energy is going to quadruple. Okay, you're squaring 2, right? So that's why it's so important. You know, that is why it's so important not to speed, right? Because your stopping distance is going to increase. So it's 950 right now. That's one type of example. Here he goes. Just a little summary that we have here. Definition of work of a given force. And then I told you about the work kinetic energy theorem. And by the way, the work kinetic theorem is a theorem that uses the work of the net force. So we talked about the kinetic energy, and then when you come back, We're going to have a break now. We're going to talk about the potential energy, okay? So any questions about that? Don't forget that we have homework there, right? If you are following, here you go. Here you go. Here you go. I posted homework for chapter 5, 4, 5. I also posted homework for chapter 6, okay? Let me see if I can move it. Yeah, here you go. I moved it. Homework 1, 2, 3, 4, 5, 6, and 7. Work and energy. If we go, let's take a look at the book. I just went to chapter 6. What are you going to do? Work by a constant force, work kinetic energy theorem. Okay, gravitational potential. And let's see if we're going to do that. Yeah, we're going to do this part here. Yeah, we're going to do that as well. Yeah, okay, good. Conservative versus non-conservative forces. We're going to do that as well. Non-conservative forces, power, other forms of energy, and the conservation. Let's see what that is. Our work done, but yeah, we're going to do that too. 6.9. Let's see, 6.8. You might want to do that. It's not much new here. I don't know why they put that in a separate, but we're going to do work by a variable force. So we're going to do everything here. All the sections here in this chapter, okay? Work done by a variable force as well. So it's 9:53 right now. Let's let us have a break. Have a break. Till 10 a.m. Any questions before you go to this break? No.
Professor,
so,
I might have missed the attendance sheet. This is Fahad.
Yeah. Okay. Wow. Let's see. What about Donia? Are you there, Donia? Remember in order to answer my calls, right? Let's see. Donia. Donia is still here, but I cannot hear you, Donia. Okay. So let's go for a break, and I see you in 15 minutes. 10:10. Come back here. No, let's see. Here you go, this one. Okay, so now we talked about energy due to motion. Now we're going to talk about energy due to position. That's how we differentiate the kinetic energy from the potential energy. Okay, so kinetic energy is energy due to motion. And by the way, there are only two types of energy, okay, that you have to worry about. Then there's another, here you go, let's put it this way. There are two types of energy you have to know. Kinetic energy and potential energy. Kinetic energy, if kinetic energy is energy due to motion, and if kinetic energy is energy due to motion or speed, right? Potential energy is energy due to position. The first potential energy that you have, there are all sorts of potential energy out there. There are several types of potential energy out there, okay? We have gravitational potential energy. We have elastic potential energy. And by the way, there are two types of gravitational potential energy. We're going to worry only about one of them. Two types. One is an approximation of the other. That is elastic potential energy. That is chemical potential energy, etc. Oh, by the way, there is nuclear potential energy, okay, etc. In this course, we will worry only about gravitational potential energy and elastic potential energy. Okay. The simplest of all, the simplest of the two is the gravitational.
Oh, Professor, you
potential
forgot to
energy.
share your screen.
Oh boy, thank you. Let's see. I'm not sharing the screen, right? Sorry. Let's see. Yeah, thank you. Yeah, feel free to remind me to talk through your mic, okay? Sometimes I don't see the messages there that you sent to me. So here you go. So there are two types of energy you have to know: kinetic energy and potential energy. If kinetic energy is due to motion, right, or speed, potential energy is due to position, okay? So we, in a mathematical sense, we say that the kinetic energy is a function, in a mathematical sense, right, of the velocity. In the case of the potential energy, we say what? We say that the potential energy is a function of the position, right? Position x of the particle. If you're talking about three-dimensional motion, then it will be x, y, and z, right? But let's keep it simple to position, a function of x only. There are two types of gravitational potential energy. One is an approximation of the other. We are going to, for the gravitational potential energy, we are going to deal with the simplest one. Okay? So let's talk about the gravitational potential energy. Okay. Let me see if I can have a little drawing here. Okay, here you go. And when I use this drawing here, okay, suppose that we go ahead, we have this mass right in here. Consider a mass M, okay, here at the surface of the Earth, right? Let me put it a G here. This mass is subjected to this gravitational force that points down towards the center of the Earth. Okay? And then what I do? I go ahead, here you go. The situation is like that, right? Here's my mass, my cell phone resting over a surface. And then I decide to raise this object here. I'm going to raise it upwards with my external force. And that's what I'm going to illustrate in this drawing, okay? So I go ahead and raise this object. Okay, using an external force. This force must be equal or greater than mg, otherwise the object is not going to go upwards, right? So when I apply this upward force to the mass, what's going to happen to the mass? It's going to move upwards, right? There you go. Going to move upwards, let's say a distance delta r. And here you go. Now I can, even better, instead of delta r, I'm going to call that delta y. That's the vector displacement. Notice that this object moved from the ground. I'm not going to call delta r, I'm going to call it delta y to remain consistent with the y-axis, okay? Notice that the object here moved from one place, from one position to another, right? The ground, y equal to 0, and then, a height delta y. Okay. And also notice another thing, very important. During this process, the work done by this force was negative, right? However, the work done by the gravitational force was negative. Okay, work done positive, work done negative. Okay. Every time that the weight, what you have to know, every time that the weight, I'm not talking about any force, I'm talking about just the weight. Every time that the weight does negative work, it has the capability of storing potential energy in the object. That's very important. Not every force is capable of doing that. Okay? There is a special type of force out there that are capable of doing that. Friction cannot do that. Friction does not add energy to an object. Friction only subtracts energy to an object. Okay? This force here that I'm using to propel the object I can say that it is adding energy to the object, but it's not necessarily adding potential energy to the object. What's adding potential energy to this object is this one right here, is the weight. And like I said, There are only a few forces that are capable of doing that. Okay, so let's write that down. Here you go. Consider an object being consider an object at rest at a height of 0 meters on the surface of the Earth. Okay? This object is subjected to the force of gravity mg. Okay? An external force is applied to this object. An external force greater or equal than mg, greater or equal than mg, comma, is applied to this object. And it starts to move upwards. Okay. Force F greater or equal than mg is applied to this object, which starts to move upwards. Oh. At a height delta y, the object comes to rest. Okay? Symbol. The object comes to rest. So when something like that happens, when some note C, okay, note C that during this process, right, the work done by F is positive and the work done by mg is negative. You know, there is a special type of force that every time there's a special type of force that every time it does negative work, it manages to store potential energy. The weight is one of this type of force, okay, which by the way I call conservative force. Friction, for instance, cannot add there is a special type of force that every time there's negative, it manages to store to add energy to the object, okay? To add potential, let's write it down, potential energy to the object. The weight is one of these type of forces. And this type of force is referred as conservative force. Friction, for instance, cannot add energy to an object. Instead, it subtracts energy from the object, And for this reason, we refer to friction as non-conservative force, as a non-conservative force, as a non-conservative force. So remember, there are conservative and non-conservative forces. Okay, remember that. The weight being a conservative force. So recall that the work going back, right? Going back to our thought experiment. Thought experiment, right? The work done by the weight is what? Is F times delta Y, right? F times delta Y. I'm even gonna go the next step, state that cosine of theta, right? Cosine of theta. Oops. Like that. So if you're going to write it down, the work done by mg during this process is going to be minus mg delta y. Notice here we have a negative sign. Okay. We say that because the weight did negative work, comma, it also stored energy. It also added, not stored, but added energy to the object. Potential energy. So if it since it performed the above work, okay, the weight is stored, added, right, minus the work done by mg, which is what? mg delta y. That's how we interpret the work done by this conservative force, okay? The weight did negative work, but in return, it added potential energy to the object. That's what we did. And now that the object has some potential energy, if we are smart enough, we can tap into this potential energy to do something useful. Okay? So now that the object was added potential energy, we can tap, if we are smart enough, okay? If we are smart enough, we can tap into this potential energy to do some type of useful work. Okay. Note, and by the way, note that let's write it down here. Potential energy due to the weight is going to be mg times delta y. That's the equation that you have to remember. So now we have three different equations, right? Three different definitions. The work done by a force, which is F delta x cosine of theta. We have this other definition, that's kinetic energy, half mv squared. And now we have this potential energy due to the weight is mg delta y. Do they all have the same units? Okay, I already proved to you, right? That what we have here is Newton meters. Here we have kilogram meters square per second square, which is also Newton meters. And here we also have Newton meters, right? This value here is Newton, this other value here is Newton. So all the three quantities here that we define has the unit of joules. Okay, so that's what we have, and we can solve problems. Knowing about that, we can solve problems in different ways. Now that we have defined kinetic energy and potential energy, we can start solve some problems using this idea of energy rather than force or kinematics itself. Okay, let's take a look at an example. Right. So here you go. But before we do that, let's take a look here. Here you go. Where we are, right? Work done, kinetic energy. Here you go. Yeah, work done by the final kinetic energy minus initial kinetic energy. Okay, and then don't forget this is the work done by the net force. Okay. And one example, let's go to gravitation. We're doing that gravitational potential energy. Okay. Weight done by the work done by gravity, by the force of gravity. And we can, let's see here, gymnast in a trampoline. A gymnast spring, let's do this example, right? A gymnast springs vertically upwards from a trampoline as in figure 6.12a. Here you go. The trampoline here. Gymnast leaves the trampoline at a height of 1.2 meters and reaches a maximum height of 4.8 meters before falling back down. All heights are measured with respect to the ground, ignoring air resistance. Determine the initial speed V0 with which the gymnast leaves the trampoline. Okay, that's what he's asking you to do. Makes sense? Let's illustrate the situation. So here we go. See here. Okay, so here we have the gymnast. I'm going to okay, here's the trampoline. The gymnast is right here. 1.2 meters, right? Let me clean up this everything here. And then he's jumping upwards. He's 1.2 meters. Going back here you go. Initial height is 1.2 meters. Maximum height is 4.8 meters. Here is 1.2 meters. Here's 4.8 meters. When he's right here at this point, he has this initial velocity V0. Initial velocity V0. Okay, when he reaches the top of the trajectory, he has this final velocity 0, right? And then we have this vector position, vector displacement that I'm going to call delta y. during the whole maneuver, he's subjected to the single force mg, which is the weight. So just drawing the trampoline. Here you go, like that. That's the situation. Here's 4.8 meters, here's 1.2 meters, right? I'm even going to put it here, it's gonna be, why not? Why not? And then we have this other YF. That's how you set up your problem. Okay. All heights are measured with respect to the ground, ignoring air resistance, which, by the way, is a non-conservative force. It's like air friction. Determine the initial speed V0 with which the gymnast leaves the trampoline. Okay. So what we're going to do here, we're going to use the ideas of potential energy, kinetic energy, and the work kinetic energy theorem. Okay. That's what we're going to do to solve this problem. Let's do that together. Going back to the work kinetic energy result, right? Work of a net force, can you remember that? Is equal to final kinetic energy minus initial kinetic energy. Right? But don't forget the work done by the net force. How many forces do you have applied to the object, right? The moment that he leaves the trampoline, the only force acting in the gymnast is going to be the mg, right? So in this special case, the work done by the net force is going to be the work done by the weight. There's just one force being applied, which, by the way, is going to be mg, final position, minus initial position, which is equal to final kinetic energy minus initial kinetic energy. Let me see here, final position. Let's see here. Let me see, work done by the, wait a minute. The work done by the mg, wait a minute. The work done by the mg is gonna be minus that, right? Because the object is moving upwards, remember? Going from here to here, the work done by the mg is going to be negative, right? Make sense? And now we can go another step here in this problem. Let me show you something interesting. Okay, I'm going to here write that equation, distribute those values. Okay, you go plus right in here. Look what we are going to get. We are going to get the following. We get the following. We can pass this term to the other side. When we do that, we switch the sign, right? And then we pass also this term to the other side. And when we do that, we end up switching the sign as well, right? So look what we have here. We have initial kinetic energy, M plus mgy naught. Mgy naught is what we call the initial potential energy. Make sense, right? At that initial height is the potential energy at that initial height, or the initial potential energy. Here we have something similar. We have the final potential energy, or let's say the potential energy at the final height. So you have initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. Okay, so here I'm going to write that down for you. Initial potential energy, final potential energy. Don't forget that this also is final kinetic energy, right? I just dropped the final in there, but that's what it means. Do you notice what's happening here? What we have here is what we call a conservation statement in mathematics, okay? What we have here is what we call conservation statement in mass, in mathematics. What does it mean? You know? Okay, so what conservation means? Conservation in physics means conservation in physics and mass means the following. What you have at the beginning is equal to what you have at the end, okay? So here you go. Kinetic energy plus potential energy at the beginning is equal to kinetic energy plus potential energy at the end, okay? This sum that you see, the sum of kinetic energy plus potential energy has a name, and it is called the mechanical energy. Okay? But let's continue here. We haven't finished solving the problem yet, right? So going back here, kinetic energy, initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy, right? You already know that the final kinetic energy is going to be 0 because the guy is at the top, momentarily at rest. You also know that the final potential energy is going to mgyf, right? The initial kinetic energy, we want to know the initial kinetic energy. It's not that we want to know the initial kinetic energy, we want to know the initial velocity. So in order to know the initial velocity, we have to find out the initial kinetic energy, right? Actually, you don't have to find the initial kinetic energy, you're going to see why. The initial potential energy is going to be mgy naught. Why you don't need to find the initial kinetic energy? Because the mass term here is going to cancel out. Okay, that's why. And we have this relation. Oh, it didn't cancel, Emma. We want to know V naught. We know Y naught. We know YF. We know G, right? You go. Like that. I'm going to put G in evidence here. Okay, let's see what we gotta do here. Yeah, I'm gonna cancel out that. That's gonna be negative. And that's gonna be positive, like that. Let me see if I have it right. Yeah, no, I don't have it right. It's gonna be all the way around. Yeah, it's gonna be like that. And then we can finally solve this equation as being the square root of what you have on the other side, okay? So that's one type of application of the concept of work and kinetic energy. Here you go. If you apply everything there, you're gonna get the value. Let's do the math. And Donnie is here, right, Donnie? Go. So let's do the math. Equal square root 2 10 meters per second square times 4.8 minus 1.2 meters. Close parentheses, what I'm getting 8.48. 8.48 meters per second. Is that what we have in the book? I got 8.48. Well, he's getting 8.40. Why is that? There's a reason for that. Right? Why do you think they got a value that's different from mine? It's slightly different from mine. It's no big deal, the difference. Okay, it has to do with the 10 meters per second square. I use 10 meters instead of 9.8, right? If you use 9.8, I get exactly 8.4 meters, like the book got. And 48, we go 8.4 meters per second. So that's one example that we have here. Conservative forces versus non-conservative forces. Okay, so what you have to know about conservative forces and non-conservative forces. Conservative forces are forces that have a potential energy associated with them. Not every force is a conservative force, okay? There are only 2 conservative forces that you need to know in this course. Gravitational force, and the elastic force. Those 2 forces are conservative. What's the elastic force? Okay, the gravitational force, you already know that gravitational force, here you go. The weight, right? Weight equal to mg is the conservative force. What about the elastic force? What's elastic force? Okay, elastic force is the force of a spring given by, elastic force. Force given by minus kx. Okay, we have seen that before, remember? Notice that this force here does not depend on the position. Okay, although, here you go. Notice that the weight does not depend on the position, but the elastic force does, right? Notice that. Now, one more thing. Even though the weight does not depend on the position, here you go. Even though it doesn't depend on the position, comma. its potential energy. That's right. Remember, I wrote down that the potential energy due to the weight, right, is what? Potential energy due to the weight is equal to what? mgy. That's the position dependence right here. In the case of the elastic force, it's a little bit more difficult to derive. In the case of the elastic force, right, its potential energy is given by, you have to memorize that. We cannot derive that here in the classroom because it requires calculus. The potential energy due to a spring, or the elastic potential energy, is equal to, here you go, I'm going to emphasize, plus half kx squared. Okay? So here you go, going back here. This object here at different heights, you know, has different potential energies. At this point here, in the space, it has one potential energy. At the lower here, at this other position here in space, it has another potential energy. At another position here in space, it has another value of potential energy. What about the elastic potential energy? The elastic potential energy, I'm going to need to do a drawing here for you. The elastic potential energy goes in the following way. Let's see if I can find a drawing here. Oh, here you go, right in here. That's what I want. Yep. Yeah, here you go. That's the elastic force. The elastic force is the force that this spring applies to a mass in the horizontal direction, right? So here you go. When we stretch the spring adds potential energy to the mass. So here the mass has one potential energy. Here the mass has another potential energy. At this position of equilibrium, we say that potential energy of the mass is zero. Okay? One potential energy here, another potential energy here, and so on. Okay? That's what you have to know. And the potential energy of the spring, again, is given by half kx squared. We cannot derive that here because it requires calculus. Okay, 10:54. Let's go another 5 minutes. Yeah, let's go another 6 minutes. Conservative versus non-conservative forces. Already covered that for you. The weight is a conservative force. The elastic force, okay, the elastic spring force is conservative force. The electric force is also conservative force, but you don't have to worry about that now. Okay, so here we go. What about non-conservative forces? Okay, we can solve problems. Right now, we did the problem just on conservative forces. What if we have a non-conservative force? Right, let's see here if you have a nice. Okay. How do we solve problems using non-conservative forces, right? How so far we solved problem only using conservative forces. What if we have a non-conservative force? What if we have a non-conservative force? How do we solve our problem? How do we solve our problems? Well, we do that. The answer is we do that using the work kinetic energy theorem. Okay, that's what this chapter is all about. This chapter is not about work. This chapter is not about energy. This chapter is about the work kinetic energy theorem. That's what's going to solve every problem that you have out there. Okay, so if you have to, so you should be able to memorize the work kinetic energy theorem. The work done by a net force is what? Final kinetic energy, right? I'm going to emphasize the final velocity here. Minus initial kinetic energy. There you go. That's what you have to memorize. And then you have to know that there are only two types of forces, right? There are only two types of forces. What was that? That is the conservative forces, and there is also the non-conservative forces. I'm going to put NC here and C here. Okay? Weight is a conservative force. Elastic force is a conservative force. You know, the friction is a non-conservative force. The force that my hand acts in an object is a non-conservative force as well. And that's how you solve problems using that involves conservative and non-conservative forces. 1058. So let's see if we have something else here. Conservative force, gravitational force, elastic spring force, elastic force, non-conservative, static and kinetic frictional force, resistance, tension, normal force, propulsion force of a rocket. They are all non-conservative forces. There are very few conservative forces. Okay, very few. So your best bet is just to memorize what are the conservative forces. In this course alone, like I said, all you have to worry is about those two conservative forces. Okay, and then the next thing here, conservation of mechanical energy. Okay, conservation of mechanical energy, as you saw before, has to do with the work kinetic energy theorem. Okay. By the way, mechanical energy is conserved. Mechanical energy is conserved only when the work of non-conservative forces is equal to 0. Okay? If, well, I can prove that to you, right? So here you go. Don't forget, here you go. The work of conservative forces can be written down as minus the final potential energy plus the initial potential energy, whatever potential energy it is. Don't forget that here is final kinetic energy, and here is initial kinetic energy. We did something like that before, right? So notice that this equation can be rearranged in the following way. This potential energy, this final potential energy, when it goes to the right side, becomes positive. This initial potential energy, when it goes to the right side, becomes negative, right? Okay, so I'm going to factor that. Okay. Let me finish that. I will answer your question. Okay, Lydia, hang in there. Okay. So even that, so we have this relationship. We have this relationship right now, right? Notice that I can pass this term to the left side. When I pass it to the left side, I'll keep them between parentheses to emphasize the fact that I have initial potential energy. Okay? At this very moment, this term here that you see is what we call the mechanical energy that I mentioned to you, right? Here is mechanical energy. Oh boy. Mechanical energy. And I will represent the mechanical energy by the letter E, and I'll put it E naught. And this term here is the final mechanical energy. Oh, let's put M better this way. ME for mechanical energy. Note that if WNC is different of 0, is not 0, mechanical energy is not conserved, right? So we get conservation of mechanical energy only when this term here is equal to 0. Okay, so when am I going? I'm gonna put that soon. Okay, so you want the recordings on YouTube channel? Yeah, I am a little bit behind posting the recordings, but now that you mentioned, I will start posting them. Okay, I guess I have the recordings only up to the first exam. Is that right? I believe you have the recordings that only after the first exam. It's 11:03 right now. Let's see here. Let's take a look at the book. Here you go. That's what this chapter is all about. Okay. Potential energy. Okay, let me illustrate that. If there is no friction whatsoever, you know, here you get a sled, right? Sliding over this track. There's no friction whatsoever. The initial kinetic energy is 0. But the potential energy is 600,000 because this sled is very high. If there is no friction whatsoever, the sum of those two terms are going to be the same. A little bit lower, you know, the kinetic energy increases from 0 to 200 because the object is now lower, the potential energy decreases as well. So what we're doing here, we are using the potential energy, we are converting the potential energy into kinetic energy, into velocity. Okay? As the bobsled as the sled goes lower and lower, kinetic energy increases, potential energy decreases. Okay, that's what it's all about. And we have this other example right in here. That's the case of in which mechanical energy is conserved. There is no friction in there. Here too, right? Work of the non-conservative forces is 0 because we are neglecting air friction. Physics of giant roller coaster. Again, final mechanical energy is equal to initial mechanical energy. So the work of non-conservative forces is going to be 0 as well. Okay, here you go. Non-conservative forces, they work kinetic, and they work should be work kinetic energy theorem, right? They spelled that out correctly. Okay, and do they have? Okay, here you go. They do have the non-conservative force. Let's see. Let me see. Let's work at this one quickly, right? 0.2 kilogram rocket in firework displays, launches from rest and fall, launch from rest and fall in erratic paths to reach point P. Point P is 29 meters above the starting point. In the process, 425 joules of work is done on the rocket by a non-conservative force. So he provides you the value of the non-conservative force. So you have to account for this non-conservative force by the burning propellant, okay? So the burning propellant of the rocket is a non-conservative force. It is adding potential energy. It's adding energy to the projectile. Ignoring our resistance and the mass loss to the burning propellant, find the speed Vf of the rocket at point P, okay? So here you go, the work done by the non-conservative force that we know. And he wants, again, what he wants, find the speed, final speed at that height. So what you gotta do, you gotta find the final kinetic energy, right? And that's what he's doing here. Here's the final mechanical energy, here's the initial mechanical energy. And then you solve, you substitute the value of the non-conservative force right here and find the final velocity. That's 6.6. What we're going to do next is going to be power. But we're going to take a break right now. Do you have any questions? The exam is still scheduled for November 2nd. Okay, so let's have our break till 11:25, right? So I see you in 15 minutes.